Welcome to month 2 of the Senior Engineer track at Bistec Hearts Academy. This session is where things get real. Last month, we focused on system design fundamentals. This month, we're going deep into distributed systems, specifically event-driven architecture, saga patterns, and observability. These aren't theoretical concepts. Every production system at scale deals with these challenges. By the end of this session, you'll have the practical knowledge to build a working event-driven system with saga orchestration and distributed tracing. Here's how the 4 hours break down. We start with fundamentals, event-driven patterns, and why events beat synchronous calls in distributed systems. The second hour dives into saga patterns because distributed transactions are the genuinely hard part of microservices. The third hour is implementation time, building for communicating services. And in the fourth hour, we look at observability, run demos, and wrap up with offline milestones. It's a full day, so we'll keep the theory tight to maximize build time. 5 outcomes for today. By the end of this session, you'll be able to design event-driven microservices with proper domain boundaries, implement both choreography and orchestration saga patterns, set up OpenTelemetry distributed tracing across multiple services, build observability dashboards, and document service dependencies in a way that a new engineer could understand your system on day one. These skills transfer directly to your day job. Distributed systems are the norm now, not the exception. Let's start with the fundamental question: why events at all? When service calls service B synchronously, you're creating a coupling that will bite you. Service B goes down. Service A is broken. Service B is slow. Service A is slow. You can't deploy independently. Cascading failures become the norm. Events flip this. The publisher fires an event and moves on. It doesn't care who's listening. Consumers process at their own pace. A consumer failure is isolated. The event is still in the queue. You can add new consumers without touching the publisher at all. Think about this. In your current systems, where have synchronous calls caused reliability problems, payment timeouts, third-party API failures, database contention? These are the classic answers. Event-driven design isolates those failure domains. The rule of thumb is this: use events for cross-domain state changes and asynchronous workflows. Keep synchronous calls for queries that need immediately consistent data. There are 4 main patterns in event-driven systems, and each serves a different purpose. Event notification is the simplest, a lightweight signal that something happened. The payload is minimal, just an order ID, maybe a status. The consumer fetches details if it needs them. Great for triggers and status changes. Event-carried state transfer is richer. The event carries the full state snapshot, so the consumer has everything it needs without making an additional database call. This reduces coupling at the cost of larger payloads. Event sourcing is a fundamentally different approach. Events are your source of truth. There's no mutable database table. You replay events to reconstruct state, powerful for audit requirements, temporal queries, and debugging production issues by replaying exactly what happened. And CQRS, command query responsibility segregation, separates your write model from your read model. Commands mutate state. Queries hit optimized read projections. Use it when you have high read volume with complex query requirements. Here's the hard problem. You have an order that touches 4 services. Either all of them succeed or you need to roll back. But there's no distributed transaction coordinator in a microservices architecture. That's the whole point. Sagas solve this. A saga is a sequence of local transactions where each step publishes an event that triggers the next. If a step fails, you execute compensation transactions in reverse order. Choreography is decentralized. Each service knows what events to listen for and what to do. There's no central coordinator. Simple, resilient, but hard to visualize the overall flow. When something goes wrong, debugging requires tracing events across multiple services. Orchestration has a central saga coordinator, a state machine that drives the workflow. It knows every step, handles failures, and triggers compensations. Easier to understand than monitor, but the orchestrator is a coordination bottleneck and a single point of failure if not designed carefully. Both approaches are valid. The choice depends on your team's preferences and the complexity of your workflow. Let's make this concrete with an order processing saga. In the happy path, 5 things happen in sequence. The order service publishes an order created event. The inventory service receives it, reserves stock, and publishes stock reserved. The payment service receives that, processes the payment, and publishes payment completed. The order service updates the order to confirm. And finally, the notification service sends the customer a confirmation email. Now the compensation part, what happens when payment fails? We have to undo what already succeeded. The inventory service releases the stock it had reserved. The order service marks the order as cancelled. The notification service sends a cancellation email to the customer. The critical design rule is this: every step that can succeed must have a corresponding compensation action. Design your compensation transactions before you write the happy path code. If you cannot describe exactly how to roll back a step, you haven't designed it properly yet. You need a message broker. There are 2 main choices in this space. Kafka is a distributed log. Events are stored on disk in a topic, partitioned across brokers. Consumer groups each maintain their own read offset. They can replay from any point in the log. Kafka excels at very high throughput and event sourcing use cases because the log itself is the data. RabbitMQ is a message queue. Messages are routed through exchanges to queues based on binding rules. Once a consumer acknowledges a message, it's removed. RabbitMQ excels at complex routing, priority queues, and traditional task queue patterns. Both require idempotent consumers. At least once delivery is the guarantee. You will receive the same event more than once due to network retries, consumer restarts, or broker rebalancing. The standard solution is to track processed event IDs in Redis and skip any event that has already been handled. Before you write a single consumer, design your event schemas. A good event schema requires 4 mandatory fields. The event ID is a UUD that uniquely identifies the specific event occurrence. This is your idempotency key. Consumers check this before processing any business logic. Version enables schema evolution. When you add a field to an event, you bump the version. Consumers must handle both version 1 and version 2 simultaneously during rolling deployments. Never remove a field without going through a deprecation cycle. Correlation ID links all events in a single business transaction. Every event in the order saga shares one correlation ID. This is what your distributed tracer uses to stitch spans together across service boundaries. Timestamp records when the event occurred, not when it was processed or stored. Always use ISO 8601 format in UTC. Here's the architecture you're building. A client hits an API gateway, which routes to the order service. When an order is created, the order service publishes an order created event to the event bus. 3 downstream services consume from the bus. Inventory reserves stock, payment processes the charge, notification sends the customer email. Each service is independently deployable via Docker. Each has its own database, no shared state, no shared tables. They communicate exclusively through events on the bus. This is the core microservices principle in action. Each service owns its domain, its data, and its events. The event bus is the only integration point between them. Once you have 4 services, debugging requires distributed tracing. Without it, you're flying blind when a request is slow or fails. OpenTelemetry is the vendor-neutral standard for instrumentation. A trace is the end-to-end journey of a single request across your entire system. Within a trace, each service creates a span representing its unit of work. Spans are linked by a trace context that propagates through HTTP headers and message metadata. The waterfall diagram shows what Jaeger visualizes for you. The order service took 50 milliseconds to receive the request. Inventory reserved stock in 30 milliseconds. Payment took 200 milliseconds. That's where you'd investigate a latency problem. Notification completed in 100 milliseconds. Total end-to-end, 380 milliseconds. Without tracing, you'd be adding logging to every service, correlating timestamps manually, and spending an hour figuring out what caused that 200 millisecond spike. 3 pitfalls will trip you up. When building distributed systems, duplicate event processing happens because at-least-once delivery is the norm. Network retries, consumer restarts, broker rebalancing. You will receive the same event twice. Your handler must check if it already processed this event ID before executing business logic. Out-of-order events happen in partition systems. Events within a Kafka partition are ordered, but across partitions they are not. Stock released might arrive before stock reserved in edge cases. Use sequence numbers or check current state before applying an event. Missing compensation is the most common Saga mistake. Every step that mutates state needs a compensation transaction. Map the sad path before you code the happy path. The solutions: store idempotency keys in Redis, route failed messages to dead letter queues for inspection and replay, and implement sequence validation in your event handlers. Observability has three pillars: metrics, logs, and traces. Metrics are numeric aggregates over time: request rate, error rate, P95 latency, queue depth. Prometheus scrapes these from your services on a schedule. Grafana visualizes them on dashboards and fires alerts when thresholds are breached. Metrics tell you that something is wrong. The error rate spiked at 1432. Logs are structured records of discrete events. They tell you what exactly happened. With structured JSON logs that include a correlation ID field, you can search across all 4 services and find every log line related to a single order's journey. Traces stitch that journey together visually and show you where time was spent across service boundaries. The key insight is to correlate all 3 using a common correlation ID that flows through every event, every log line, and every trace span. Your event schema already carries it. Make sure your services include it in every log entry and trace attribute. Here's the challenge for this session: 100 points across 4 deliverables and 3 hours to build. 25 points for 4 communicating microservices in Docker: order, inventory, payment, and notification. They must communicate exclusively via the event bus. 25 points for the event bus setup: Kafka or RabbitMQ configured with persistence, schema versioning, dead letter queues, and event replay capability. 25 points for distributed tracing, OpenTelemetry instrumented across all 4 services with end-to-end traces visible in Jaeger or Zipkin. 25 points for a service dependency map, Saga flow diagrams, failure scenarios, a service catalog, and an operational runbook. The passing score is 75 points. Exceptional work scores 90 and above. 4 pitfalls will cost you time if you're not aware of them. 2 fine-grained services. If your inventory service is calling a separate stock level service synchronously, you've created a distributed monolith with extra network hops modeled by business capability. One service equals one bounded context from the domain. Ignoring event ordering, events within a Kafka partition are ordered, but across partitions they are not. If order-related events end up in different partitions, you can receive them out of sequence. Missing compensation logic. Every happy path action needs a compensation. Draw the sad path first, then implement it before you write a single happy path handler. No idempotency. You will receive duplicate events. Code defensively from day 1. Check event IDs before processing anything. The flip side of each pitfall is a best practice: domain modeling, schema versioning, failure first design, and chaos testing in your development environment. The scoring guide is straightforward. Exceptional means production ready. Your tracing is configured with sampling strategies, your dead letter queues are monitored, and your event schemas support versioning. Proficient means the core functionality works with only minor gaps. Developing means you've hit the requirements but with rough edges, and the passing score is 75. For offline milestones to complete before month 3, add event sourcing to the order service, implement CQRS for order queries, add circuit breaker patterns to all services, create chaos engineering tests, implement an event versioning strategy, and document your async API specification. These aren't required for this session's assessment, but they'll make you significantly better prepared for month 3, which covers advanced patterns and production deployment strategies. The required reading: Sam Newman's Building Microservices, specifically chapters 4 and 11. Chris Richardson's Saga pattern documentation at microservices. I/O is the definitive reference for Saga design. The OpenTelemetry specification at OpenTelemetry. I/O has SDK quick starts for every major language. For tools, Apache Kafka is the industry standard for distributed event streaming. Jaeger is free and easy to run locally for distributed tracing. If you want a higher level Saga orchestration framework, look at Tempora. It handles state management, retries, and compensation logic automatically. Eventuate provides event sourcing with Saga support for teams that want to go deep on that pattern. Distributed systems reward those who design for failure from the start. Event-driven architecture, Saga patterns, and distributed tracing aren't complexity for complexity's sake. They're the toolkit that lets distributed systems fail gracefully and recover automatically. There you gain practical skills to design event-driven architectures, implement both styles of Saga patterns, instrument services with open telemetry, and reason clearly about distributed system failures. Month 3 goes into advanced production patterns, service meshes, circuit breakers, and deployment strategies. Great work and keep building.